All right, good afternoon, everyone. I'm Gregor Duval, work for CGG, and I'm part of the G&G support group for the multi-client division of CGG. And this afternoon, I'm going to be talking about broadband seismic data, and really to follow on the talks we just had, because before you drill a well, obviously, it's all about de-risking before you drill the well. So hopefully I'm going to be showing that broadband seismic data gives a plus really to help de-risk the prospects on the South Atlantic margin. And I'm going to inspire myself from two main surveys that we've recently acquired, one in Brazil in the Santos Basin, and the other one on the Angola side in the Kwanza Basin. So so I'm going to start with well, this is the content of the presentation, so I will be starting with some introductory remarks, just to remind ourselves really, why do you want broadband seismic data? Why do you want that for the seismic interpreter point of view? And what happens to your seismic data from what you used to look at before on the conventional data? And I'm going to be introducing the surveys and the acquisition parameters. And then in two steps, I'm going to talk first about the Presalt exploration and what the broadband seismic data have to bring on the table to explore these plays. And then I'm going to be talking about the post-salt plays, so above the salt, and post-salt deposition. That's the way we actually hear it. And also what it can bring in terms of reservoir characterization. So starting with some very simple remarks, and some of you may have seen these slides, but I think it's very good to remind ourselves the purpose of having broadband seismic data. So, I mean, in an ideal world, your seismic data would be imaged with basically one single spike for every event you'd be looking on your seismic. And this is basically what we are trying to achieve. This is what we are trying to push the seismic towards. And if you look at a very basic wavelet model here, and you start by adding some more high frequencies in this wavelet, what happens is that the central peak of that wavelet actually is narrowed down. It becomes sharper. But on the other hand, what you see is that the side lobes of that wavelet, that always accompany the wavelet, are actually more pronounced because you've introduced more high frequencies. On the other side of the frequency spectrum, if you add more low frequencies, you actually reduce those side lobes, but you widen the central peak. So it's easy to see that by combining the two, by increasing the bandwidth overall from the low side of the spectrum and to the high side of the spectrum, you actually push your seismic towards that ideal single spike that you're looking for in your seismic data. So reducing the side lobes and narrowing the central peak. This is an example, some data we acquired at the time, some test data, 2D data offshore Gabon. And this is looking simply at the seabed here. So you have the conventional seismic data and the broadband data down here. So what you see is there the wavelet extracted at the seabed level. You can see two prominent side lobes on the conventional data, while here the side lobes have been basically flattened. And you can see these side lobes actually interfere with your interpretation, and you've got many outcropping events here at the seabed that you can very clearly see on the broadband data. So these side lobes have been removed and help to better interpret the data. And when you think about it, you look at two side lobes and one central peak on the wavelet. So basically, in a simplistic way, you're looking at 2/3 of your seismic reflections, which are actually not useful. They are not wanted for your interpretation. When you look at it in the spectral world, and this is the same data in Gabon here, so you have the conventional data again and the broadband data. So that's the conventional spectrum here, so typical bell shape dominated by one frequency here. But now with the broadband data, the broader range of frequencies up to 150 hertz and all the way down to 2.5 hertz. That is hard to see here on the scale, but believe me, it's about 2.53 hertz. Now you can see you have actually the slope of the Q absorption of the Earth. This is you can see that you lose the high frequencies faster at depth as the signal penetrates the Earth. So you lose your high frequencies, and it is actually represented by that slope. And this is something you wouldn't be able to see on old conventional data before. And you can see also the dominant frequency is actually now more skewed towards the low frequencies. And the low frequency here on that image is what gives you that texture. We call it the texture of the seismic data. It's almost like you're looking at some kind of shaded relief section here, and it's all down to really the low frequencies that give you the texture, the envelope of the formation. So you have a better feel of what the stratigraphy is on the fly when looking at the seismic data. So now, the seismic surveys I'm going to be using in this presentation. One is a large 3D survey that we acquired in the Santos Basin. Well, in fact, a bit on the transition from the Santos Basin there into the Campos Basin north. And this is directly northeast here of the recent Libra and Franco discoveries, major discoveries in the Presalt. And you can see it's located outboard here with only a few well streets, so in a fairly unexplored area and unlicensed, as you can see here on the map. So this survey is about 14,000 square kilometers, and we acquired it with a streamer spread of 8,000 meters streamer length with 10 streamers. It in fact acquired in 2 phases. We had 2 vessels coming in, and the second phase was acquired with 12 streamers. The broad size profile here was from 10 to 50 meters, the cable profile. And I'm not talking about the technology here in this presentation, but I'd be happy to answer any questions if you have. And this is the way we acquired the seismic data, the broad size data, with a variable depth profile for the streamer. Streamer separation 100 meters, and as you can see, all the other parameters. Maximum depth output, we processed it with the pre-stack depth migration algorithm, and here the images you're going to see are actually the Kirchhoff migration. Now the Angola Kwanza Basin data, so in fact 2 sub-surveys, and one is in fact covering block 21, the recent Kamian discoveries. So I have a couple of cross-sections to show you in this presentation. The other one is just south in block 22 there. And these are the acquisition parameters. Again, 8 kilometer streamers. And then you can see also processed with pre-stack depth migration algorithms. So the examples you're going to see are in fact the CBM depth migration. The block 21 survey is actually not finalized yet, and the examples I have here are actually fast-track results. So where are they located? And it's been mentioned earlier. You know, the conjugate margin story. This is where the surveys are actually located in comparison to each other. So in fact, the Angola Kwanza Basin is not the direct analog, it's more the analog of the Campos Basin on the other margin. But we have very good similarities already with the Santos and Campos Basins to the Kwanza Basin. So you will see that in the seismic sections. Here is the correspondence in terms of stratigraphy again, with the pre-salt reservoirs we mentioned earlier in the other presentations, the coquinas and the microbiolites below the salt, and also you have the in further places towards the north, the transgressive sands here that you can find further in Gabon, for example. So this is the diagram already illustrated earlier to show the correspondence. So I'm just going to skip through quickly. And then start talking about the pre-salt exploration. And before this, I compiled together just to show a bit of the exploration history, which was talked a bit about earlier again. But I compiled this from our well database, so it's probably not exhaustive, but some of the discoveries or uncommercial discoveries, at least oil was found actually in the pre-salt. And you can see that there are actually in the Campos Basin in Brazil some fields actually that were found back in the late 70s, early 80s. And they were found in about 100 meters waters, so they were fairly easily accessible for drilling at the time. And now, more recently, the exploration has moved into the very deep waters, around 2 kilometers of water there, as the technology progressed. And you can see here, this is the major play opener Lula discovery in 2006, multi-billion barrels, as many of you know, and followed by subsequent other discoveries. And more recently, Franco and Libra, also both multi-billion barrels discoveries. There are major structures directly underlying the salt. Next. And now in the Kwanza Basin, you can see also, again, some fairly early discoveries, call them discoveries, but oil was retrieved in the Presalt section there in 200 meters. And then we moved into the deeper waters, 800 meters, where the Baleia well was drilled not far from the more recent Cameo discovery. And then subsequently more discoveries in the deeper waters. So you can see as the exploration moved into the deep waters, big discoveries were made. And one thing to keep in mind is also that looking at the geology, as the base salt flattens with major structures giving relief there, this is where some of the really big discoveries were found as we moved into the deep waters. So before I show you some seismic, this is a quick diagram to show the concept, to understand what the broadband seismic data is going to bring you to interpret the pre-salt plays. So typically you would have the base of the Aptian salt here, or the breakup and conformity, then truncating some fault blocks below in the South Atlantic. So you have your lower Cretaceous fault blocks here. And these simple straight blue lines are basically your reflectors as you would image them with conventional data, band-limited data. So they don't have much character. They have the same thickness, in fact, here in this diagram, so you can't discriminate them from one another. And when you start interpreting one as the top of your formation, the question is, where next can I correlate this horizon on the seismic? Where is my formation top? With the help of broadband seismic data, and especially with the low frequencies penetrating deep into the earth, it gives you that texture that I talked about earlier. And the texture gives you this, basically, and it helps you to correlate reflections across the faults which have been truncated, where you don't know how much offset you may have. So this is an example of some legacy data to start with in Brazil, to compare with the broadband seismic data that we've acquired in the area. So this is the legacy seismic. And in fact here, what we've had to do for this comparison is the data were processed with pre-stack depth migration, the broadband data, so we had to stretch that back to time to compare it. So since it's not, there is also an element of processing in there. What I did is then look at the pre-salt by basically filtering the broad-size data, the broadband data, truly to show you what is coming from the broadband and not from the illumination side. There might be some discrepancies when you compare a new survey broadband data with an older survey, different acquisition parameters, things like this to consider as well, which bring the uplift in the new data. So here, I'm simply filtering the broadband seismic data back to fit the conventional spectrum that you would have on these legacy data. And this is what you get here for the salt here and the base salt imaging. And then you've got these fault blocks down there. The thing is that the question is how you interpret this deep section here with the fault blocks. When I bring in the broadband data, and I can compare that back and forth like this. So the, sorry. So you can see the texture and the low frequency is actually coming through there a lot better And one thing you may have noticed is actually the correlation of these deep stratigraphic packages here, which is a bit more difficult to identify there on the seismic section. You don't exactly know how to correlate all this. So there is then the kind of interpretation you can make with your top salt and then the base evaporites, and you can identify, well, the base of the sag sequence or tops in rift there. Another example now in Angola. So we're looking now at at block 21. In fact, here this is the Kamian structure. So these are the fast-track PSDM data, and I filtered it to show you what conventional data would look like again. And this is the actual broadband data, conventional and broadband data. Sorry, I'm struggling a bit with the sheet. Yeah, there we go. So, and again, you've got the texture, lower frequencies, bring you the image at depth. And this is then the kind of interpretation you can make. And you can actually identify their really thick sag sequence in the quanta base in there. And this is the structure there of Cameo discovery. A major tilted fault block there. The really steep dips here, probably coming from the kitchen area there on the deep with the migration of oil into the trap there. And another image from Cameo. So again, filtered broadband data and broadband, truly broadband, again, filtered and broadband data. So this is where the Cameo structure sits here. And again, you can see that really steeply dipping fault block. And that's the kind of interpretation you can make. So then, now looking at the post-salt section and the benefits of the broadband seismic data, and essentially to look at here facies mapping. We were talking about stratigraphic traps earlier. So it is important to know exactly what the facies look like and how you can actually characterize them with the seismic data. And we've done also a bit of reservoir characterization on the seismic data in Brazil, so I will show you these examples as well. So to start with, and looking at facies, we found that on the Santos 3D broadband dataset, there are some volcanics. Actually, you can clearly see on the seismic data. And when you look at the South Atlantic gravity map there, and you see where the seismic data actually sits, it's right at the tip, the north extension of the Abrolhos volcanic complex. The Cabo Frio high comes through there. So these volcanics, they can be seen here. So you have massive intrusions through the dataset. They're very clearly imaged with the broadband data with a very nice pure black reflection indicating the top, the increase of impedance on your seismic data. And here the base. On the broadband data, I don't have the filtered version here to show you, but what you would see is the side lobes actually come through really strong with the volcanic intrusions there. So it's always a bit difficult to actually see which is the top, which is the base of your volcanic intrusion, especially when they are really thin and tuned on the seismic data. We found also structures like this. For example, here what we think is a relic volcano, and you can see it's associated with some extensional faulting and some volcanic intrusions found deeper here with the salt structure there. So it's probably been injection of volcanic materials, and that small volcano actually appeared at the time on the seabed. And if I zoom in or take another direction here, you can see here that volcano, and it's a really strong reflection at the top indicating that it is a very clear marked increase of impedance there, and really deep also in volcanic intrusions through there that you can see. So if you zoom in, you can in fact see several phases of the growth of that and the formation of that volcano there. So may have some impact as well on the maturity of the source rock, on trapping mechanisms, or things like this, which we are now able to see with the broadband data very well. Other things like in the shallow, in this example, this is the Atlanta discovery in the Oligocene here. And what you're looking at here is, if I can see that, yeah, so a very clear marked flat spot. And again, without the side lobes that you would typically see, you would see normally a white, black, white as your flat spot here. So this is the top of the reservoir, and you can see also very sharp imaging of the faults coming through there, through the reservoir. So obviously they are very important to characterize properly and see how far they actually propagate through the seal to identify any potential seal breach and de-risk your prospect. And see also how deep they actually are rooted to identify any potential migration routes. So this is again the Atlanta discovery. And if I zoom, I believe I have a zoomed in version, and you can see the contact very clearly. You can see how the top reservoir brightens up here. So it comes from near zero impedance to a really soft reservoir, indicating the presence of hydrocarbons there. And this is the flat spot through there. And this is, in fact, then the base of the reservoir. So you can see the flat spot. Well, it's not flat anymore. It's basically because the reservoir is filled to base here. So you've got an entirely filled column there. And if you take a time slice through the flat spot, here is what you can see on the broadband data. And here again, I've brought in the conventional data, the legacy data in the area. So you can see the marked improvements imaging these faults here, cutting through the reservoir, especially through there, there. And then a bit of mapping of the bright amplitude anomaly associated with this discovery. So this is now the Adept structure map that we've been able to identify on these seismic data. And these are the anomalies. They are related. You can see the faults coming through. So these anomalies are actually coming through really nicely on the broadband data. And what we did also on this field is produce an acoustic inversion. So it's using the post-tag data and trying to extract from this data some more quantitative values of impedance. And very importantly, what we did is we used the initial model as the seismic velocities, so which are mainly the low frequencies you would get from the seismic data. And here we've applied a 2 to 5 hertz filter, so using the really low frequencies of this broadband data to produce that initial model for the inversion. You've got a couple wells here, so you can see actually how they tie in with the initial model. And then we produced an inversion on the conventional data and on the broadband data to compare. And I've got them in a larger view here. So this is the results on the conventional data. So low impedance are appearing in blue there, and higher impedance in red. You can see how it correlates with the well data. And then this is the results on the broadband data. What you see is a better correlation with the well data. So these are purely blind test wells, so they haven't constrained the inversion itself. And you can see already a better calibration at the end. And what you see is that essentially the low frequencies, they bring in more stability to the inversion, and they allow you to give a more quantitative result to your seismic inversion. So they're really important there. And the high frequencies, they help actually to image very clearly the wedging out of the oil reservoir there. Because with the limited bandwidth of the conventional data, what happens is you have some tuning effects on the edge of the structure, which may impact then the results of the inversion. I'm going to skip that, and just to illustrate here, what we've brought in with the broadband data is typically when we need an initial model on for the seismic inversion, we need to bring in usually information from the well data. So we would extract that low frequency thread from smooth logs or after a low pass filter on the well data, and use that as the initial model. But now with the broadband seismic data, with the addition of these low frequencies, we fill in that gap. So this tells us that in areas where we don't have access to well data, you can rely better on broadband data to give a better inversion results. For quick look AVO inversions or post-stack inversions, you should rely better on the broadband seismic data themselves without any calibration. Useful for frontier areas where still yet we don't have any well data. In the Kwanza Basin, other challenges, very complex salt here. And this is the image we got from the block 22. So in block 21, you look at a salt which is quite deformed, but doesn't produce any major overhangs and canopies like you can see here. So this look more like the Gulf of Mexico. And you can see how we achieved actually to image the lower reflections underlying the salt with overhangs here with the depth migration. And I mentioned the Gulf of Mexico here really to show you the benefits of the broadband data. We have then removing any challenges from the illumination. We're only using 2D here, and this is the conventional data, and it's just showing you the raw benefit of broadband data here. Sorry. Here are the broadband data, and you can see the extra low frequencies that actually help to image these structures here at depth related to the salt. So those low frequencies not only penetrate deeper, but they also help to image better through the salt. Still in the block 22 area, broadband data also will help then to better characterize the facies and any hydrocarbon-bearing reservoirs. So this is an example here with a DHI, which we looked at a bit closer. And here we are using now the PSTM, the time data, because we are going to be looking at what the frequencies in time have to bring in. And recently, we invested in a very nice piece of software which basically gives frequency decomposition of the data and then allow you to blend dominant frequencies together to highlight where they actually interfere constructively and destructively in other areas. So I've highlighted here the really low frequencies of the broadband data with these frequencies, and then combined together, this is clearly highlighting the gas cloud we could see on the seismic data. Another example is also looking at the channels we find actually in the postal section, and which are very important to track and see actually where they trap relating to the salt structures. We use also the frequency decomposition to produce these images, and it's using also the very low frequencies, which wouldn't be available otherwise in conventional data. And you can see amazing details of the channel structures coming through there. And this is, for example, here a channel wrapping around a major salt structure there, and you can see it meandering through there, and you can see various phases, some kind of braided channels there. And you can see also probably some splays coming off it. So you can see details like this. And here you can see various phases of growth of these meanders characterized by various dominant frequencies, which each relate to different facies probably, so sands or shales deposited in the channel. And this is one last image also to show again these channels through there. And you can see also that you're probably looking at things like a flat here where the channel actually meanders a lot, and various phases of incisions because the slope is not that important, and as it comes around the major salt structure, the dip is more important, so your channel is actually straighter with a really straight incision, and then it starts meandering again, where it starts flattening out down deep of the major soil structure here. So as conclusion, the overall benefits really from broadband seismic data is that it gives you the more of the genuine formation signature, because it doesn't have any side lobes and has a sharper central peak. It gives a strong basis for reservoir characterization, post-stack and pre-stack seismic inversion, so more stability, better quantitative results. And the low frequencies penetrate deeper in the, through the earth to give a better image of the thin rift fault blocks and the pre-salt plays you would be looking at on the South Atlantic margins. The high frequencies give you the really the sharpness, and also help you to image the facies variations in the post-salt section and the major turbidite plays that we're exploring in the South Atlantic as well. With this, few acknowledgements. Jaswinder, Lauren, and Steven, who actually helped contributed to this presentation, and CGG multi-clients for the permission to show these examples. Thank you.
Very much, Gregor. Excellent. Now, I might not have relinquished block 21 if I had that data. That was really good. Right, now we have perfect timing. We have some time for questions. Yes, Keith. I'll just wait for that microphone.
How much more expensive is it?
We can discuss afterwards. It's a lot more than. The fact is that when you look at the technology, in fact, what's involved is there's no new equipment really. The technology that we've developed essentially involves the same equipment but deployed differently. So in terms of acquisition costs, it's pretty much the same. And
so what's the key difference? The streamer being towed deeper?
So the streamer is towed deeper. It's got a curved variable depth profile. So from I showed in the early slides from about 10 meters to 50 meters at the tail. And for this, obviously, we use steerable devices to steer the streamer in depth and laterally as well. And we use also solid streamers, which are commonly available in the industry, to help actually reduce the noise, especially on the low end of the spectrum. So these, these tools are available. It's essentially the method that we've developed, and also after that, the processing technology that we developed to go with it. And it's all about, and to explain it simply, about removing the ghost from your seismic data. That's where it lies. Where we've been limited before in terms of the frequency spectrum, is the high end of the spectrum was limited by the notch where the ghost reflected from the surface back down interferes destructively in the frequency domain. So this is what limited the spectrum before, and we've done some developments to remove the ghost from these data. So this is the way we use the variable depth profile of the streamer to remove the ghost. So there's a bit more going on the processing side as before.
Very good. Thanks for the explanation and the question. Any other questions out there? Yes, there's one at the front.
What's the situation with onshore broadband?
Onshore broadband. I'm afraid, actually, that's not a question I'm able to answer. Obviously, it's a very different environment, but I know we've done some latest developments to bring in more bandwidth in the onshore as well. So we've done some developments on the vibrator side. I don't know if any of you guys, Adrian, if you would be able to answer the question better than I am. But we've done some developments as well on the, and it's more from the source side, as I understand.
Any other questions from the floor? So, I mean, it looks like a really neat technology. Is it now beginning to get accepted and used globally? For
It is
Presalt,
starting
Gulf of
with-
Mexico, Santos?
Yes, so we've acquired, well, as you can see, so Santos Base in Angola, and we are acquiring a major wide azimuth survey in the Gulf of Mexico. And it's involving, you know, several vessels, a really large acquisition over there, and Broadband seismic. We've acquired a number of surveys in the North Sea already. And also in the, on the proprietary basis in the west of Shetland in Norway, a number of other surveys. Basically around the world, we've done quite a few surveys also in the
I just wonder if it was
Western
helping with
Australia.
things like pre-basalt imaging, Western Shetlands, and then down into Rockall. And
I didn't bring the examples here, but we have some 2D lines that show some improvements. It's not day and night like, you know, you're seeing the basalt all of a sudden coming through for you, but it's bringing more low frequencies at depth to identify the fault blocks. So now we claim we have actually acquired over 100,000 square kilometers of broad-size data around the world, proprietary and multi-client data.
no,
So,
that's
good
excellent.
experience.
Nice technology, and I think I can think of a few places that would be very helpful. Thank you very much.
Thank you.
Thank you.